Get out your notebook.
That's so rude. I feel bad.
All right, next thing I'd like you to do is I'd like you to read the side that says forces and interaction. I want you to start on the side that says forces and interaction, section 5.1. Go ahead and read section 5.1 to yourself. Okay, tell your partner what an interaction is. That's all. All right, right here. Austin, tell me about interaction.
So, if you push against the wall, you can't like push against the wall, try to push them down.
Yeah. So the key with an interaction, right, is forces always come from objects. And to have a force, you have to have a pair of objects. And there's going to be a set of forces, right? So there's the example that he gives in the reading is leaning against the wall. Because if you lean against the wall or you put a force on the wall puts a force back on you, right? If you try to push a heavy cart, right, the cart pushes back on you. That's because you can tell that it's pushing back. Right? It's hard to get it moving. Okay. All right. So finish this up by reading the other side, which talks about Newton's third law. All right. So to make sense of the third law is, in some sense, it's the easiest law to get wrong, I think. So let me make sure I'm recording. Okay. All right. So the third law, I think, is the easiest law to get wrong. But we have written down here, right, that Newton's third law says that when one object exerts force on a second object, the second object exerts an equal and opposite force on the first. So that's true. But it only makes sense in context, right? So I want to draw your attention to this figure down here, right? The best example I have for third law is a rocket. How does a rocket work? Well, a rocket works by pushing its fuel backwards, right? So a rocket pushes fuel backwards, and therefore the fuel pushes the rocket forward. That's how that works, right? You can also think about this in terms of walking. How do you walk? You push your feet off the ground, right? So to walk, you have to push the floor back so the floor can push you forward, right? If I jump, how do you jump? You push the ground down, the ground pushes you up, right? One other thing here, so do this, like if you pound on your desk as hard as you can, right? Your fist hurts. Why should your fist hurt? You were putting a force on the table. Why does your fist hurt? Because the table puts a force on you, right? That's the idea of the third law, and it always follows that rule. It always follows that rule that if one object puts a force on a second object, the second object puts a force on the first object. You've probably heard this before, and every action has an equal and opposite reaction. That's a good shorthand way of saying the law, but I want you in your notes to actually write down this one, because this one here. This is the most important explanation. So Newton's third law, last one, I am on there. So Newton's third law, whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first. I guess think I've read that. Yeah. Do you think we're going to be back to normal school next year? You want to put money on it? No. If I want to summarize this law in one word, the word that I use is interaction. So you'll notice you've got 3 laws, but what I've done is I've circled in each one. I circled one word or one equation that summarizes the whole law. Yeah. Force on the first. I'm taking this right off of here. I just copied this thing. So the reason why I circled those, or I put a box around those things, is what you eventually need to remember. If you can't like remember all the words, that's fine. But what's important that you remember is that first law is inertia. Second law is about net force, mass, and acceleration. And third law is about interactions. To wrap up this this section, what I'd like to do is I'd like to show you a few video clips and ask you to think about them.
Wait.
I need this.
Okay.
Anybody else still need this?
No. It's in our paper.
Yeah.
Our pop out.
All right. Here's what I'm going to do. I'm going to show you a video, and then you're going to pick one of the laws. It doesn't matter which one, but you're going to pick one of the laws and tell your partner how that law applies to this video. What's that?
An object in motion stays.
No, so just tell your partner which law you would apply here and how you would apply it.
There's the
That push did more than just some bread.
object in motion stays in motion.
All right, Vincent, which law would you apply here? Let me ask you this. Why does he keep moving? Why doesn't he turn?
This tire is bad. This is pretty much a bad job.
Right, so the idea is there's not enough friction in the tires, right? So there's not enough force in the tires to do what? To stop, to give you a net force, right? You have no net force, so what do you do when you have no net force? You keep on going in the same direction, in a straight line, right? So I think first law is easy to apply here. Any other laws I could apply here? Wes?
Use the third law to involve reaction car.
So again, why did the car stop? The car didn't stop because it hit the wall, right? Because the car put a forward force on the wall. It's not the forward force that stopped the car, it's the backward force from the wall. So the wall hit the car, or the car hit the wall, and so the wall hit the car.
It's so weird though.
Yeah.
It keeps going.
He was fine.
You kidding me? They do this for
All right, next one.
It'll be all right. It'll be all right. It'll be all right.
Pick a law and explain to your partner which law you think applies.
Second. An object in motion. Wait, no. First, third, I guess. No, just first.
All right, Alexis, what do you think about this one? Between first and third, I think you could make a case for either of them. Pick one and make a case for it. Tell me why the first one. Right, once he's off of the motorcycle, right? There's no more force acting on it, but he keeps going, right? As a matter of fact, you can see that he keeps going about the same speed as the motorcycle because an object in motion stays in motion.
They probably wait.
Anyone got another law you could apply? By the way, the key is when I ask questions like this, so all laws can apply all the time. So it's more interesting how you apply the law than if you pick the quote unquote right law. I'm gonna try it.
For the third law, it's
I mean, when he falls, right? Why does he stop falling?
because when he hits the ground,
Yeah, again, the fact that he hits the ground, that's not what stops him. He puts a downward force on the ground, but the ground also puts an upward force
Look,
All right, this is my favorite one.
oh no. Third law. Wait, one more time. Watch this one.
All right, so pick a law and tell your partner why that law applies.
All three. Here's why. You get the equal opposite reaction when it falls down the wall. You get the acceleration mass. Because the reason you went so far from the wall is because you didn't weigh that much. You had a lot of
All right, Matt, you want to pick a law for us?
NPL.
Third law, explain.
The cat hit the wall and it's driven and forced to the wall.
Yeah, so the cat at the wall at the cat, you can kind of see the bat, you can even see a little bit of bounce there, right? Yeah. So, all right, third law, anyone else? There's actually another third law application. Yeah,
When she jumped on the guy.
yeah, how do you jump? Remember we talked about how do you jump? You push down on the floor, so the floor pushes up on you. Any other laws?
All of them.
All right, you want to give me an explanation for another one?
Okay, so the first one is no, not really.
Because you're right, you can always apply any law, right? We can apply the first law here because the cat was in motion until acted on by a force, right?
Do you think he broke his neck?
The other thing I would say is what happens, another way to explain the force is what is the force causing when he hits the wall? Causing the cat to do what? No, he can't die. You bounce back, but there's a term I'm looking for. Accelerate, right? Stopping is an example of acceleration because you're changing your speed. So you can also say that force is causing an acceleration. So the second law. All right, two more. Oh, I forgot their sound.
Oh,
Wait.
he was branding.
Branding.
That's why you build bigger walls. No, you have to brand the horse.
All right, tell your partner what you think which law applies. Long, yeah.
I can watch that movie,
Yeah.
That's so terrible. I never even let my enemy.
The second one.
That's so disgusting, bro.
All right. Sam, you want to pick a law for us?
That broke him hard.
Bro, you gotta think.
Vincent, you would try.
Is it?
Oh, second one.
Yes, second.
Okay. Why?
Okay, so you know how you want to say?
No.
Alright, so you see our steering school right now, right?
Okay.
So when the horse kick you, like forcing you to go the direction that yeah.
Yeah, so the kick was a force that caused an acceleration that points in the same direction, right? He put a force backwards and the acceleration was backwards. Yeah, I'll give you that.
Imagine you got
Any other laws we could apply?
turn it off.
Go ahead. Isaiah.
No horse kicks him, his body acts on the horse.
Yeah, now, and I want to be clear about that. That's a good use of the third law. Let me be clear about that because I want to make sure to point out a bad use of the third law that sometimes I heard. This wasn't what you said. What you said was right. So there's sometimes people say, oh, the action was he branded him, and the reaction was the horse kicked him, right? That's not, from a third law perspective, that's not what we mean about action and reaction, right? That might be what we mean by from a biological perspective or from a psychological perspective or something. But from the physics perspective, we need something like Isaiah said, right? That if the horse kicks, or the horse puts a force on the guy puts a force back on the horse. So the idea is the horse can feel when he kicks him, right? Like if you kick something, you feel it being pushed back, right? You can tell when you kick something.
I hate walking.
All right. One more. I got two versions, so I'm gonna-
Hello, I'm Johnny Knoxville.
Oh, yeah.
That's my rocket skates.
Well, it's all gonna be weird, but it's gonna fall on
Nah, I don't recommend trying this at all.
Well, you're so serious about it too, man.
This will get a little faster than the last one. So why, these are different bottle rockets? No, just more of them.
They all ran away.
All right, so anyway, rockets. There's one law that I want to make sure to apply here to rockets, that always applies to rockets. Actually, tell your partner, and this is one of the few ones that there's one answer I'm looking for that's better than the other. So all answers are okay, but there's one law that I'm looking for that's more important than the other one. So tell your partner what you think the most
I think
important
it's
law
Newton's
is.
second law of acceleration.
Because he wasn't.
I don't know. Jake, which law would you apply here? Okay, tell me why. Okay, net force of the rockets would accelerate him forward. Okay, I'll give you that. There's one I'm taking that's exactly correct. But there's one I'm looking for in particular. Yeah. Tell me why.
Because like the rocket, like after
Yeah.
outer that way,
Yeah.
and then the reactor of the rocket.
Yeah. So this is all right. Yeah, the second law absolutely occurs. We can also make a first law argument. But what I want to point out about anytime you have a rocket, the whole point behind a rocket is that a rocket pushes fuel backwards so that the rocket can go forward. Or if you got like an actual rocket, the rocket pushes fuel down so it can go up, right? That's the basis behind any rocket, any jet engine. Honestly, even to any like sort of propeller. Right? Think about a helicopter. What's the point of a helicopter? Why? So the helicopter pushes the air down, and so the air pushes the helicopter up. Okay. All right.
Much more